Hey Honors Physics guys, I am here to discuss sort of the background information for your truss project. So first off, let's discuss what a truss is specifically, or remind you of a truss. A truss is a connection of triangles, and the reason that we use triangles really to define what a truss is and build trusses from is that shape easily seeks equilibrium. So this might be a simple truss sitting on, say, the foundation of a house or something like that. But if you think about a truss as basically that ladder, so this is a step ladder like this. If you apply a load up here at the top, meaning you're trying to stand on this ladder, these legs are going to want to do this, right? It's because by you standing there, you are pushing into this leg, and you're pushing into this leg. So the ground tries to push up, etc. And the net result here would be that those legs want to kick out. So what do ladder manufacturers do? They put a little thing right there. And by doing so, that ladder will stay in equilibrium until you've exceeded the possible load that goes on that thing. So basically this part right there might give way, or in worst case scenario, you might overcome the strength that actually exists in that aluminum structure. So the general idea of static equilibrium, meaning the equilibrium that you can get to applied under a load, is where if you added up all of the possible forces, they're not going to give you an acceleration. You don't want an acceleration in static equilibrium. You want all of the forces, the sum of everything, to equal zero. So that means the sum of the vertical forces, the sum of the horizontal forces, the sum of the twisting forces, and all that jazz. Those things all have to equal zero, and that structure should stay there for a given load. You exceed it, all bets are off. So that's the general principle behind your structure, which you are building, which is this truss. It doesn't need to look exactly like that, but so let's move on. The first thing you need to do is you actually have to identify a geometry that can actually be analyzed. Now, when we know that we need to take a look at all the forces, the sum of all the forces, in this class we are only looking at the sum of the vertical and the sum of the horizontal. So that means that when we look at the structure, if we could add up everything that's, say, pushing up and down and pushing side to side, that we could probably determine really what the max load is. But that might not really be the way that we want to go about this. So think about it like this. You're not going to be hired as a bridge engineer if you tell the people that hired you that you're going to make a bridge out of as much material as you can so it can hold as much as it can. The way it actually works is you design for a specific load. So if you pick a geometry that can actually be analyzed, and I'll explain that in a second, you build that structure for the load that it's intended to hold. So what I'm going to say right now is, whoever told me to build this bridge, they told me that it needs to hold 50 pounds. It needs to. That means it needs to stay in equilibrium with 50 pounds added to it. So I'm going to put 50 pounds right there, just hanging. Sound good? Good. So now what we need to do is analyze the structure itself really quickly to make sure we can even calculate the forces there. And this is something that's called deciding whether or not your bridge is statically determinate, which means that do the number of joints where the members actually connect to each other, do they exceed the structural number of members, or at least a ratio? So the static determinacy formula is this: 2j equals m plus 3. So the j refers to a joint, the the m refers to the members. So let's take a look. We have 1, 2, 3 joints. 2 times 3. Does that equal the number of members? We have 1 member, 2 members, 3 members. So does that equal 3 plus 3? And we know it certainly does. So that means that this little structure, this truss, is actually capable of being algebraically solved for. It means that the forces that show up when you apply a load are actually going to be solvable. So here's what we do. We draw our structure. It's a free body diagram, a big one. Put that there and there and there. I have my little foundations where the thing is sitting, and I have my load here, which is 50. I am in good shape. I'm going to label A, B, C. Those are just joints, and this is the standard thing. You label joints counterclockwise. Okay. So here's what we do. You start where you know something. Now, while we certainly know 50, we don't know if other forces are pushing up on that or anything. So really the force that's contained kind of in CA, we don't know that. And we don't know CB. And you could say the same thing about here. We don't know CA and we don't know AB, but we know absolutely how hard the ground is pushing into A. So if you draw a free body diagram for A, what you see is you have an upward push, and that's coming from the ground. You have a vector that goes from A to C, and you have a vector that goes from A to B. So that's a little free body diagram that represents the joint right there. Question is, what is the value of this? If you think this is 50 pounds, this is your hand, and this is your other hand. If you're being asked to hold 50 pounds, each hand here must push up with a value of 25. Okay? So now, we go back to the idea. This thing, we can use some algebra to determine the forces. We have a free body diagram that we're already getting used to setting up algebraic expressions for, given our other problems. So here's what we get to do. We get to start with the fact that we have a 25 on the y-axis. We get to sum vertical forces first and set them equal to 0 because there's 0 acceleration at this point. We're saying that point A does not move up or down at all. So, decide what's vertical. 25 is positive, isn't it? It's pointing right up. And then if you look at AC, while AC is diagonal, it contains this little vertical piece. So we say plus ACY, right? Meaning, if you look at AC, it has to have some vertical piece to it. Is there anything else? No. AB is horizontal, so we get to set those equal to 0. Well, by this point, you should know that AC's vertical component, we've done this repeatedly in things, is sine theta. So let's say theta here is 40 degrees, 40 degrees. We're going to say AC sine 40 equals 0. So, if we're solving for AC, it ends up being AC equals negative 25 divided by the sine of 40. The answer is negative 39. So if we are hanging 50 pounds up there, the force that is inside that member AC is negative 39 pounds. So negative, huh? That's weird. Negative is actually attributable to something in engineering. Come over here to this little guy, this 25. If you've said that the ground here is pushing into that structure with a positive 25, and you've kept every other sign consistent to that positive 25, when you get a negative, it refers to a type of force that is called a compression. A compression is a squeezing force. It's if you put a pencil on a table and pushed down on the end of the pencil, if you put your hands on two sides of a ruler and pushed inward, it would bow, it would bend. If you took a piece of spaghetti on the lengthwise and you put it between your fingers and pushed in, it would bow and it would snap. That is a compression. Now, that's only part of the problem. Remember that the big idea here is that the sum of all forces equals 0. So we just did the y forces equaling 0. So now we have to do the x equaling 0. So you do that at each joint. So here's what we know. AB is on the x-axis. So we could name that just AB. If you want to say x, you can, but it's just on the x-axis, so it would be AB cosine 0. Plus, well, nothing from the 25, right? That is vertical, so it doesn't have an x component. But if you take a look at AC, it does have an x component. So you say ACX. That's all that exists there. So you set it equal to 0. So AB plus AC cosine 40 equals 0. And here's the cool thing. You already know what AC equals. So I'm going to say AB plus our negative 39, because that's what AC equals, multiplied by the cosine of 40 equals 0. So AB minus 30, 29.9 or whatever, equals 0. So AB is equal to 30 pounds. That means when you when you apply 50 pounds up top, we have this nice compression of negative 39 pounds in member AC, but AB has this positive 30 pounds. That is positive because it's a different type of force. We've already used this term before. It's a tension. So just like we talked about with that ladder, that if you're stepping on it, the legs will want to kick out, and there's the little piece in between that holds them together, that piece would be in tension. And if you notice how a ladder is built, the legs of the ladder are much, much, much bigger than that little piece that connects the two legs. And that's because an object that is in tension is so much stronger than it is in compression. Think about a meter stick. If you wanted to break a meter stick by pushing down on it, so you kind of hold the thing vertical, take your hand and you push down on it, it'd be really easy to snap it, just like that piece of spaghetti. If you try to pull apart that material, So you just try to take your two hands and pull it without kind of twisting it or anything. It'd be nearly impossible. Same thing with a piece of spaghetti. Think of how hard it would be without kind of twisting it to snap it. How hard it would be to just pull a dry piece of spaghetti apart. So anyways, this is the introduction to truss analyses. This is an engineering principle used in mechanical engineering, civil engineering So this process is used by mechanical engineers and civil engineers to analyze the structure for a given load. So here's the beauty of this. That could be 50 marshmallows, 50 tons, 50 pounds, 50 kilograms, 50 newtons, 50 U, and the two results that we got are the exact same unit you began with. So you analyze a geometry for a specific load, and then you have to build it. So if this was in fact 50 pounds and you're building this triangle, AC would need to be able to hold 39 pounds in compression. You'd have to put something there that could actually withstand that force. Now, as structures get more and more lengthy, so a common truss design might be this. So if you have a structure like this, which is much more like a bridge, and it's sitting on those ends, you still have that 50 pounds, you would begin right where you did. And what you'd realize is you'd solve for these two members. Now, it seems like this might be complicated, but what you end up doing is you go to the next joint where you have the fewest unknown things. So if you look at this joint, you don't know this, this, or this. But at B, you only don't know this one and this one. You've already solved for this. So when you set up a free body diagram for that joint, it looks like that, and like that. You label it A, B, C, and that one goes off to H. And then you do the same process. Some of the forces in the Y, some of the forces in the X. And sometimes things, for instance, like BH, which we know is positive, well, there's no other Y force. So BH actually has nothing on it. There's no load on it, but it needs to be there for stability. BC in this case is going to be equal to a negative BA. Okay? So, once you solve for those two, you'd move on to H. So that's how you progress through a truss analysis. I hope this helps. This is part of your project process. I'll see you in class.